My name is Srinivasan, and this is Lab 3 Black Hole for Physics 2211. So for the introduction, there are two main parts to this experiment, and they are interrelated. In the first part, we will be calculating the mass of a black hole by analyzing a computational model that represents a star orbiting the black hole, which reveals the gravitational interaction between them. In the second part, another computational model will be used, and the initial velocity of the spaceship needs to be calculated so that it will go around a black hole without crashing into it or a nearby planet. And some related fundamental principles are that Newton's universal law of gravitation and the momentum principle. For a brief overview of the lab results, the mass of the black hole was 1.48 times 10 to the power of 34, and initial velocity of the spaceship was negative 9.6 times 10 to the power of 6 and 9.5 times 10 to the power of 6 meters per second. Here are some models representing the principles. So using Newton's second law, the following equations can be derived. And the parallel force is the force which determines whether the object speeds up or slows down, while the perpendicular force is the force which determines the direction of the object. And some fundamental principles and respective code are shown here. So for example, we have the calculating the mass of the black hole, calculating the parallel force, Newton's second law, and also the perpendicular force. So for the reasoning, since the parallel and perpendicular forces are components of the net force, a change in either will result in the net force changing. Final velocity will be used in place of average velocity due to the fact that universal gravitation is a non-constant force. Since everything takes place in space, the only force really acting on objects comes down to gravitational forces. For the ship, the force of gravity due to the black hole and the force of gravity due to the planet will be acting on it. For the star, the only force acting on it is the force of gravity due to the black hole. And here are the initial conditions and systems and surroundings for part 1. So the system is the star and the surroundings are the black hole, and the initial conditions are shown in the code. And here's the code for the iterations and the update formulas. So the update formulas are like the position and velocity update. And then here are the results. So F net was equal to 9.864 times 10 to the power of 48. And then the parallel force was equal to 3.6 times 10 to the power of 28, and the perpendicular force was equal to 9.1 times 10 to the power of 28. The mass of the black hole is calculated to be 1.48 times 10 to the power of 34, and to get the mass of the black hole, the average of numerous values for the mass were just averaged together. So what does it mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular forces? The net force is not any different from the rate of change of momentum. They are the exact same, and they have been used interchangeably in the lab. This is because the net force, or the sum of all the forces acting on a system, is equal to mass times acceleration. And then shown below, we pretty much derive how they can be interchangeable. So acceleration is equal to velocity over time, momentum is equal to mass times velocity, and the change in momentum over time is equal to mass times velocity over time, which is just mass times acceleration, which is equal to force. Rate of change of momentum is equal to final momentum minus initial momentum over change in time. So for part 2, systems and surroundings, the systems and surroundings are that the system is the spaceship, the surroundings is the black planet and the black hole, and then the initial conditions are given in the code below. So part 2, for calculating the net forces, for both net forces, we just have to evaluate fundamental equations discussed before, such as r hat, and universal gravitation. So the gist of it is that we calculate the force of gravity on the planet by the black hole, the force of gravity on the planet by the spaceship, and then we add those together for the net force on the planet. And then for the net force on the spaceship, we just do the same. So part 2, iteration in Newton's second law. This code right here basically shows how to apply Newton's second law in the position update formula to make the planet and spaceship move. And here are the results for part 2 of the lab. So the initial velocity of the spaceship was found to be negative 9.6 times 10 to the power of 6 in the x component, and for the y component, it was 9.5 times 10 to the power of 6. The shortest distance between spaceship and black hole was 0.34352 times 10 to the power of 10. And possible areas of error in the experiment are that the calculated mass could have been closer to the actual mass if the program ran for longer, giving out more individual masses for the black holes, which could have then been used for a more accurate average. And then for part 2, some possible errors were that the velocity values may not be accurate due to the fact that the mass of the black hole was rounded and the gravitational constant was also rounded. And I used guess and check technique for finding the initial velocity of the spaceship, so this may not have been the most perfect velocity and messed up what the closest distance to the black hole could have actually been. So for the what if, what initial velocity would the spaceship need in order to enter into some kind of orbit around the black hole? The spaceship would need to have an initial velocity that's more focused in the y direction, making it more vertical, and this can be achieved through changing the velocity of the spaceship to be similar to the planet, except with a lower magnitude in the x direction and a greater one in the y direction. So again, this is kind of done through guess and check. So the initial conditions for the spaceship are shown below, and the picture to the right shows that it made a complete orbit.